Hello. Here we go. This should work. Let me check up here. I think we are live, right? If somebody is watching, they can let me know. All right. So let me take a sip here. So what are we going to do today? I need to implement this. I already got some stuff running here, but if we run the tests, we will see it's not passing because, well, I only get these two functions implemented. But we need a bunch more. So the bigger picture is, let's see. What we want to implement, or what I want to implement in my compiler, is liveness analysis in order to implement this algorithm for register allocation. And this paper here, which is pretty nice, it's short and sweet. It has 18 pages. It says up here. So this paper has a pretty cool or easy to understand linear scan algorithm for doing register allocation. One of the requirements, though, is that you need to have liveness information about your program. So, if you have a program like this, where you say A is B, then if this, go here, if not, go here, blah, 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 blah. You need to annotate this source code or this IR with liveness information. And so the compiler knows this variable is live from here to here. Because from here to here, because it's defined and here's the last use, or here, we need to annotate the IR with liveness information in order to know, and this is why this is important, in order to know whether we can put two variables in the same register. So if you have, say, A and B, and they're live at the same time, meaning they will be used later on, they cannot be in the same register. But if two variables are not live at the same time, you can put them in the same register. So this is what register allocation is about, right? A computer like an x86-64 has 16 general purpose registers that we can use. Some of them are already gone because it's the stack pointer and blah, blah, blah. So we cannot use them, but we have, say, 12 left, and we want to use those registers because registers are fast as hell to access and to write. So instead of keeping stuff on the stack in memory on the RAM, we want to keep it in registers. But limited resource. So which stuff do we put in registers and which not? That's what's called register allocation, deciding what goes into registers and whatnot. In order to do that, again, we need to do liveness analysis. So I started reading this paper here in to do register allocation, and it even says we need liveness information, and how old and live we need live intervals, which is it says here, this is an example for live intervals. It says that the variable a it's live from instruction 1 to 11. So A is here. And here's 11 because, here's A, here's the last, the next use. So there's a hole here. I think it says this. Oh yeah, there's a hole here, because this is now where, the last use, and this is a different A, and then A is live again from here to here. But I think if you numbered, there's a hole on this other side, because if that branch is not taken, then A is not used. But if the branch on the right is taken, then A is used. So you need these live intervals, again, to know which stuff to put in which registers or not. And the paper here does a good job of explaining, what your IR has to look like. It even has this nice data structure section, which is super rare for compiler papers or compiler books even. It's all super abstract. So the data structure section here explains, what your IR has to look like. And then it even says, this is SSA stuff, so I got this in my SSA file here. But then it explains how to compute the live intervals, which is nice. It even has, it has this algorithm for it. The problem is it uses this thing that is not defined in this algorithm. So even if we were to implement this, which is what I tried to do, you stumble into this and you go, what is S live? And then somewhere up here, it says be first, somewhere it says, I don't know if I can find it. Somewhere it says s.live or b.live. Let me see if the search function here works. B live, there it is. Every basic block, B stores in B live the set of values that are live immediately before the first instruction B first. So this is called a live in set. Live in as in live in over here. So that paper led me to finding this one here, which is the expanded version of the same section in the SSA book, and this describes how to compute liveness sets, which are these live in or live out sets, for SSA form programs, because SSA form programs have the special property that they have so-called phi functions in them, and they have different uses and different definitions. So what this paper has is a pretty daunting algorithm. It's not super daunting, but it has this algorithm to compute liveness. And what it does is post-order traversal, a depth-first search. But then what it also has is it has a nested loop tree, which is a data structure that represents loops in a control flow graph, which I think they have a picture of this somewhere. But that is a bit, daunting. And then I read on and on and on. And then if you scroll past all of this, you will see that they have another, maybe more intuitive way of calculating liveness, which is closely related to the definition of a live range, blah, 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 as we called earlier, therefore live range, blah, blah, blah. This idea was first proposed by Apple, and then they have this variant, which is apparently used by the open source compiler infrastructure LLVM, which we all know, and this is it. Like it's these two algorithms, which is pretty neat. So you iterate over every block in your CFG. You get the phi uses, which is defined. Let me see. It's somewhere in the paper, but here's the definition. Here on the left, phi uses. And you go over these, you add them to the live out set, blah, blah, blah. You union the sets and then upper mark and recursively walk up the thing. And this seems pretty doable, which is why I started hacking on this. So now I started working on this, and the current state is I started defining these phi defs and phi uses. All of this is really, really hacky code still. I don't care about, idiomatic Rust code at this point or making it nice. What I care about is making the tests down here pass. So I wrote a little test yesterday that sets up this basic CFG, B0, B1, B2, B3, and it has these vars. So here we have A1, which is live out, live when you leave this block, and then it's live in B1 and it's live in B2, but it is not live out in these, and it's not live out in here, stuff like this. So this is a good small test to check, live out stuff. So this is the only assertion I have so far because nothing works yet, and this is what I started hacking on. Oh, there's actually people in the chat. Hey, Felix. All right. There's actually somebody watching. Define liveness. All right. What is the official definition of liveness? Let me find if there's a really succinct Liveness. I don't think there is. Come here, liveness. Let me check something in my ebooks. I think engineering and compiler has a really nice. It has a good example. There it is. Can I jump to this? Yep. So a variable v is live at a point p if and only if there exists a path in the CFG from p, which is the point, to use of v along which v is not redefined. So taking this over to our example. The variable a is live at the point p, say this instruction, only, what did it say? Only if and only if there exists a path in the CFG from P, which is our point here, to a use of V along which V is not redefined. So here's P. Is there a path from P to a use of the variable A along which A is not redefined? All right, I'm bumping the font size. I think this should do it. So A is live at this point, and here it stops being live because this is the last use of A. So if we pick any other point in our CFG, say this one here, and we say, is A live at this point P? Then the answer is no, because from here, there is no path through the CFG at which there's a use, a reference to A. And yeah, so that's the shortest definition of liveness. Am I doing grad CS? No, this is me hacking on my side project compiler. So what you're seeing here is this compiler I've been hacking on in Rust for a year. And I'm doing this for, not profit, only for fun. The idea is to build an optimizing compiler that has register allocation, optimization passes, IRs, and all of this stuff. So in the past, I only did, AST to, bytecode transformation or AST out to assembly and whatnot. So this is new terrain for me. I can show you. So let me show you this. This is the middle pass. So what this compiler does is it does name resolution, which is just bookkeeping. It has a type checker. Then it builds a control flow graph CFG with the IR builder. IR is the intermediate representation. The CFG is our intermediate representation. Then we lower strings because we have strings in language. Then we build or turn the IR into SSA form. And then we do liveness analysis, and then we deconstruct SSA. And then actually, let me see where this is referenced. So this is the middle of the compiler. People call it the middle end because you have the front end and the back end. So this is the middle end of the compiler. And if you look at, so this is I think, this is the main function of the compiler. So we built the AST, we parse the code, then we put it, this is the front end, what you see here, this is the front end of the compiler. This is the middle end, and then we do code gen where we output x86 assembly, all of this good stuff. So this is what the language looks like. This is a test, so I can run this. This is, it's just a function. You define I, you have a loop, increment I, print the number, blah, 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 exit condition, print a string. So that's the language. Why have you used Rust? I do not know. My relationship with Rust is complicated. I'm not a 100% fan, but I think I started this last year with the idea of, let's just hack on something. And I saw Dora, which is, I don't have a browser open. Let me see if I can open browser without leaking. So there's Dora. Let me bump the font size on this. So here's Dora. And this is, Dora is a just-in-time compiler for, for the language called Dora. And the guy who built it, I think he's still in college. But this is pretty advanced. There's a lot of stuff in this compiler. So I started reading this, and I wanted to hack on something. So I just, said, fuck it, let's just copy and paste some stuff. Let's get a parser running, and let's see if I can build an optimizing compiler. That's, short version of it. All right, so let's see. There's actually people watching, so we should give them actually a show. So, liveness analysis. Let's do it like this. Let's close the quick fix here. So this is our test that we need to pass. We need to make pass with this code on the top left. On the left, this is our test. So this is the CFG. We have A defined. We have two branches here. Being a conditional. So imagine it doesn't matter, but let's say there's a condition here that says if true equals true, then do this on the left. Otherwise, do the thing on the right. Then both do this. So I set up the CFG by hand, the graph, with a bunch of macros and a bunch of helper functions. And then I also do this by hand, which is normally done by the name resolution step, where you do the references and you add stuff to the assignments, or by the IR builder, actually. Then we build SSA, or we turn it into SSA, which is, doing dominance analysis, dominance frontiers analysis, which was pretty fun code to write. And then we compute the life sets. So if I run this, you will see that it fails. And what we need to implement is exactly this algorithm from the paper, right? So let's bring up the paper again. It is this one here. So this is what we need to implement. I copied it over and turned it from this pseudocode into actual other pseudocode, and then started implementing it. So so this is the function we need to implement. Compute live sets SSA by use. Input CFG. What I did is I made a little wrapper function in which we iterate over all the functions in our CFG and put those into compute live sets. And then in live sets, compute live sets, this would do the actual thing. So for each v in phi uses, which are the variables used, vars used in the phi functions of a successor block. So this is what I already implement. So the phi, let's take this and move it down here so we get this right above the function. All right. So for each phi use, which is this, we say live out B is the union of this. So this is, we can implement this. So let's do it. And then we call upper mark. And then for each v used in B, phi uses excluded. Then we need to up and mark B. And then up and mark, we can build further down. Let's put it here. And upper mark then uses all the definitions. It checks whether if V was defined in B, phi is excluded, then return. If V is in the live inset of B, return, because we were already here, otherwise added to the live inset. If V is a phi def in B, return for each P, blah, blah, blah. So, where are we? We have phi uses, live out, nothing works, the test is failing. Let's just type some super stupid pseudocode. So for each E phi uses, let's do this. For V in phi use, we have this is the live outset. So let's take this, move it down here. For E live out, we say live out insert V, right? All right, so, and then up and mark. Let's do up and mark context. We need to connect. Context is, it's like a data bag, data structure that contains a bunch of stuff that you need in all of the layers of the compiler. So this is modeled after what the Rust compiler does. They also have a data structure called type context, which contains a lot of, what type does this var have? What name does this refer to? What is the name of this? Like all of the helpers that you need if you analyze source code. So up and mark, and we need to put in the context because that has a bunch of stuff, and we need to put the block in, which is our block, and we need to put V in, which is a really not cool now. Let's call it var. And it doesn't return anything because it's recursive, so that's going to be fun in Rust, I bet. Import this. Why is this not you? Or let's just, for our purposes, phi use B and log this. And then up and mark, and then we say up and mark context with block V. And I'm sure the borrow checker will now complain. Will it not? Oh, this is a place. This is another data structure that I have. So place is either register, version register, or param in a function. In our case, it's always a version register because we're in SSA form right now. So all the registers are version registers. They have a version next to them. So we put this in unused var up and mark. So this is the first stumbling block we'll run into. So if we take this and we put it in, we will see what we need to implement. So let's do it like this. We can, for example, say this is live in, and we say block ID, and then we say if live in contains V, return. So far, so good. This is easy. Otherwise, we say live in insert V. Right? That's this one here. If V is in the phi defs, let's pull this down. If phi defs contains V, then return. For each P in the predecessors of B. Oh boy. So now we get into this whole graph traversal stuff. Let's see. All right, so let's say this here is a to-do. Implement this. If the definition of B excluding pi is good, for each P walkup. Let's remove this. All right, so the borrow checker here, what does it do? Borrow check, kind of borrow, kind of is mutable. Why mutable? Yeah, we need it to be mutable, right? All right, so we have the connects here. We access live out. We don't need this, right? Yep. We can even say we concatenate this. Is this nice? All right, what is the pseudocode of this? Let's put this here. All right, and then upper mark, live out, it's gone. Now we don't log anything. We can rethink this in a moment. Then we have this down here, which we need to implement, and the stuff down there. Remove return. Okay, because we don't have any code after this. Yes, I don't know C++, but I do know C. By the way, the chat and all of the Twitch stuff is open on my MacBook, which is on the left, and this here is the Linux machine. And I use a tool called Barrier, which allows me to just move the mouse cursor to the left, and then it shows up on the MacBook, so I can remote control the MacBook, which is pretty nice. All right, so where are we? We need to implement this stuff up top. We need to, yeah, we have 3 to-dos left. So this is a to-do. This is a to-do. And this is a to-do. So what do we do first? For each V used in B, I think I have all the stuff ready for this. So each V used, so let me show you what that means. So let's do this. Let's go to this. And we do compile and run, and this prints the functions. All right, so that's cool. So let's say we have this code here, and I'm gonna put something in here to make it fail, and we run this test. It will print the CFG of this function. So this function here is this. Sorry, this. This here is I equals 0. This here is moving this in a temp register. And then jumping to this block, go to 3. Go to 3 is the loop body, because we don't have a condition, blah, blah, blah. So anyway, these are all the instructions in the IR. Each one of these is an instruction. Every instruction follows the pattern that says register equals operation. Operation could be a reference to another register. So the instruction is a move. It moves data from one register to another register. Or the instruction could be a binary operation. So target of the instruction is this register, and the instruction itself is a binary operation with the operator being the plus, and the operands being another register and a literal value, a constant. So 2 is a constant here. And on the left, for each V used in B, phi is excluded. We don't have any phi functions in here. But each V used, that means the 0 here is not a V because it's a constant, right? This one here, this is not a use, but this here is a use. This here is also use. This is a use. This is a use. This is a use. this is a use in the terminators, which is something we should write down, otherwise I'll forget it. To do, remember that terminators also use vars, which is, I think I ran into this before. So what we need to do is we need to go through all of the vars used in instructions in B and up and mark them, right? So again, the idea here is to analyze the liveness of vars. So we go through all of the uses of var and then run through this algorithm and see, look, if the thing was defined in B, then we're done, because it's not live in going into B and it's not live out going out of B. Okay, so for example, what do we have? Like 3 is defined here. Well, this is a shitty example, I guess. This, right? So here, up here in this other block, register 1 version 2, this is what this says, is defined in block 4 and it's used here. So if we traverse all of the uses in block 4, we will get to this one, right? But we will also find out, oh, it's defined in block 4, so, you know, nothing to do because it's not in the live in or live out set, which has scope to a block, right? We're not interested in that. Later on, when we implement the register allocator, where is it? Here, then we're interested in this, because then we're interested in the live ranges. But in order to do this, we need to, you know, have the live out sets computed previously. So where were we? We were here in the uses and we need to exclude phi. And I said, hey, I have a bunch of this stuff already, because in my SSA code where we construct SSA, we have to do something like this, where we say we iterate over all the instructions. There you go. There you go. We iterate over all the instructions in a block. And then we say for var in instruction reads in this block. So reads should be the uses. But what does this do? It says, oh, it puts in the block ID. Okay, so it returns var. All right. So yeah, a var is a register and a place and a block. All right, so it says if it's a phi func, return the phi operands. In our case, we would not do this. So we would say, we can type this here, right? We can say for ints in block instructions either iter. Is it iter or iter? Iter. Somebody told me it's iterate on stuff and not iterate on stuff. So let's see. For ints in block instructions iter. We want to get all of the we want to say filter I, and we want to say I is not a phi func, right? Please, no phi funcs here. Phi excluded, because these are special cases, which is why we have the phi defs and phi uses. I'm not going to get into phi functions today. So we're going over all the instructions in the block for each v used in B, phi excluded, up and mark BV. For ints in this. So now we say, what is a v? We say for v in ints reads block ID. So now we get each and we say up and mark. Oh boy, this is not gonna go well, right? Up and mark context block v mismatch type. All right, yeah, we need this. I do have function for this. Yeah. This is the okay. I just beat the borrow checker. All right, so we get this. And I'm very confidently saying this, but I have no idea. And I don't have a really strong test suite yet. And then, yeah, this. Remember that terminators also use vars. I think, let me see. Ha ha ha. Check this out. We doing terminator reads and then update vars. So we need to do the same thing here, and we say, there you go. If terminator reads. Is this always a terminator can? Yeah, a terminator can always read one var. So we say if let sum v up and mark context block v place. So this is now each v used in B, phi excluded. Traverse B to find all uses. What am I working on? I'm working on implementing this algorithm to compute liveness in my control flow graph, in my toy compiler, in order to later compute live ranges in my toy compiler, in order to then compute register allocation for my toy compiler. All right, so for each v used in B, phi excluded, blah, blah, blah. If we run the tests, yeah, still fails. Of course it fails because we never add anything phi uses. So I'm wondering, yeah, this is what's missing, right? So in the example I have, okay, so the test fails because, let me show you the test, because A is not yet in the live out set of B0. So A, this var is live going out of this block here. And the test fails because it is not in a live outset. But I was just thinking, look, I already put a bunch of code in here on the fly. Why does this not work yet? It should. But then I realized, oh, we never actually add anything to live out except the phi uses, which is, SSA related stuff. So the phi uses are the uses. The phi uses are the variables read by a successor of the current block in its phi functions. All right, these are the phi uses. If you jump definition, you will see this. Give me the successors of this block. Then give me that block. We can shorten this, I think. All right. Yep. Give me the instructions of the successor. Give me all the phi functions. Give me the phi operands. Flatten this list. Check that the block they read from is the block that we are talking about here. Give me the place. Collect this into a thing. Flatten, collect, blah. And it gives me a vector. Like all of this is, it's not the most beautiful code. All right. So the test doesn't pass yet because I think this is the kicker. All of the stuff so far is, SSA related, and this is actually the meat of it, at least for our simple use case. So let's see the reason. So yeah, the reason why, in order to mark A as live out in B, we need to look at each predecessor. Oh, okay, I see. All right, so if we're here and we say, hey, this is a read, we're reading A, then, and we're in B1, Then what this would do is it would say, give me each predecessor of B1, and that is B0. It's a predecessor. It comes before in a graph. And it says address to the live out of the predecessor. All right, so that's pretty cool. All right, so let's try and see if we can implement this. In order to do this, we need to put the func in here too. Block func. Yep. Func. Putting the func back. All right. So now let's look at our SSA code again and say pret this for each predecessor. It should be pretty easy. Do we? Yeah, we have this pre-order preds insert pre-computed predecessor chain for each block. I'm wondering, I think this is the same thing, right? Like so I'm wondering what they mean with predecessor. Do they, if I'm here, do I need to walk up here, like on the left, and also to the right, and also to this? The immediate predecessors or all of them? I think it's all of them, right? For this to work. Because say we use D here, then and D is defined further up here, then we need to walk from here to here to here to here and mark it as a live out in all of them. So I have some code. You just saw it in our SSA file where we walk the chain to the predecessor tree of the block. Preds tree. Pre-compute. You know what? Let's just copy and paste this code. What do I care? Yep, let's just copy and paste this. So what we do is to do this is duplicated from the SSA code. Preds tree, where is it? Preds tree. SSA Preds tree. Yeah. We could just can we duplicate the type definition, hash map, go on. Unused import, pre-order, we need to import this, traversal, super traversal. Unused var, let's clean this up. No, the code is not yet on GitHub. All right, so what you're seeing is me hacking. This is not cleaning up code. This is not making it tidy. I'm just trying to make this test pass. All right, so Preds tree. Let's put the preds in here. And I always want to say pretzel. For each func, we compute this. We put this in here. By the way, why do we need to pass this in? Nope, we can do this. We can do this down here. Save ourselves this thing. Computes live set is not called recursively. Function defined here, predecessors, blah, 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 traversal. All right, so for each used in B, and in up and mark, whatever we call up and mark, we need to put the preds in. That's right. So the preds is preds tree. And then here, Like I'm sure this code is ugly and it's disgusting. Function defined here. Similar typed. Where? Unused import dominance. Why? What? Remove unused import. Liveness can find Pretz tree similar time. Yeah. You know what? Let's import Pretz tree. Oh, Pretz trees. Is it Pretz trees? Trees. Oh, and I called it Pretz tree. This is it. All right. All right. So we don't use this. We can probably get rid of the func. So no, we can't. So we say for 4p in Pretz block ID. How do we use? Sorry, let me jump to this. Pretz. How is Pretz used? Get block for. Oh, there you go. For pred ID here. Can only be used in a function. You know what? Fuck it. Unwrap. Self. That's wrong. Block ID. All right. So now this is interesting. Now we say the live outset of live out of the pred. Oops. What did I do? Fat fingered stuff. Pred ID or insert with hash set new. And we say insert. It's a hash set, so we can insert as many times as we want. And we insert our V. Oh. And we don't need to do this for each. So this is this. Live out is this. And now we need to up and mark. And we say up and mark, and this is recursive, right? Because we are in up and mark. And we say context, Pretz, func, up and mark, P and V. So func, pred ID, oh boy, and V. Consider borrowing here. Yes. Yeah. Oh boy. You know what? Fuck it. We're gonna clone this. And then we say, I don't want to worry about the borrow checker right now. Alright, so we clone this, use and value Pretz. Why is oh, okay, yeah, that's right. We need a reference. So let's say pretzel. And there we go. Yep. What is this? Why is this? Okay. The test fails with what? All right, cargo test. What does it do? Cargo test. Oops. Cargo test. Middle liveness. Right, like this. And then we say, give me the Rust backtrace. Panicking. Where does it panic? In liveness 246. 246. The fuck? 184. No, I have. Geez. Okay, so this output was cut out. It just says assertion fail. All right. So, you know what I'm interested in? Is there anything in live out? So if we say context live out, and we do the debug printing, and we say context live out, is there even anything in there? There you go. There you go. Look at this. Look at this. So let's debug this, and we say block live out in context live out either, and we say we print it like this. We say live out block equals this block live out. Doesn't work because this doesn't implement the debug, the normal. All right, so it says, let's zoom up here. All right, so it says live. Aha, wow, okay, cool. All right, I got it. So first thing why I just said, okay, cool, is I construct a CFG by hand here on the left, and I put in these register IDs by hand instead of using the register counted. These are just numbers. So I put them in by hand so they're readable and I know what stuff refers to. So A is 1,000, right? If we search over here for 1,000, I just searched for 100, you will see that it actually is in the live out set of 0. But this one down here, does it contain this? Does not work because this is a version register and what I have on the left is a not version register. So I'm getting excited. So the good news is it seems to work at least in some form because we got stuff in live out, which is great. But our assertion is wrong because we don't check for a version register. So check this out. So since we convert this here to SSA, but we don't have any stuff writing to multiple versions, we can simply say everything has version. Oh no, here this has version register 4000 version 1. Where is oh, we do have a phi. Of course we have a phi. We do have a phi function down here because both this block references this D and this D, so we need to insert a phi function down here. Because the value D could be coming from block 1, this D, or the value D could be coming from block 2 and this D. All right, so that's interesting. That's cool. All right. Let's see how we manage to do this. But what we can say is that live out B0 should contain A with I have a method for this. Wait a second. So A is a register, and we say A with. Wait a second. I think I have a method for this to say give me version without version with version. Fuck it. All right. So let's just say we do this by hand, and we say contains versioned register. It needs to be a reference versioned register, and it needs to be A and 0. Filter or macro. What the fuck? What? Oh. Sometimes it's as easy as fixing the syntax. The tests pass. Cheers. That's pretty cool. Hey, Connie. What's up? Yeah, all green. Let's celebrate. Okay, so it actually works. It actually works. What are we still missing? This is what we're missing. Let's implement this before we add more assertions, because I have a feeling because if you look at this stuff over here, there's a lot of stuff in live out for 0, which is stupid. Because block 0 should only have one thing in live out, if I'm not understanding everything incorrectly. Oh, and the reason is, okay, so this is, what we're missing here is an early exit. So up and mark walks up the CFG, right? So let's say here, we say A, right? And we hear A, and we up and mark is called in B1 and for A, and we say walk up the predecessor chain, right? And then walk it up and mark it as live out in the predecessors. And it does this for all of the vars. But say it does it for this, for C, right? Then it should stop and not do anything if it's defined in this block. It should not add it to the live out here, I think. All right, let's just see. All right, so let's make an assertion here. Let's make an assertion. I'll try to make this pass. So we say, fuck it, live out from this is the len of this should be 1. We only want to have one thing in the live out set for B0, right? So this should now fail. And it says, whoa, we got 8. You want 1? You're off. All right, let's make this pass. We're on a good track. I'm fired up now that we actually got this to pass. By the way, I didn't. Should I maybe drop? Is this how you say it? Drop a tweet. So I confidently just wrote on Twitter, we're live and we're 80% of the way there to implement liveness analysis, which is of course a bold lie. Who knows how many % of the way we are there? Who knows? All right. So what do we again? Let's continue with our hacky shit. So if def v is in B. If the definitions of V include B, then we exclude it. So B is the block we're passing in. So let's do a really really shitty version of this. So the other way to formulate this is give me all of the definitions done in B and check whether V is in them, right? So we could say block instructions either map I target collect hash set place let block defs. So these are all the definitions done in this block as a hash. And we say if block defs contains V, we return. If this works, like if I'm now gonna rerun the tests and it works, and I type this first try, somebody should clap. I'll get the kids and the wife and they should clap. All right, here we go. Dudes, girls. Oh, what? I do love programming. Nice. I think this is what people should clip on Twitch, isn't it? It's a thing you share and it goes viral and people say, look at that guy, first try, boom, knocks out 5 lines of Rust code, boom, reruns the test, boom, it's green. Yes. Whew. All right, so that was pretty good. By the way, let's make a stupid little commit, right? So this is what we did so far, blah, 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 blah. And we say, quick save, first test assertions passing. And this is, I'm not gonna lie to you. I'm not gonna clean this up. This is my pet project. I'm not gonna clean this up. You should see my log messages. Look at these log messages. Actually, it doesn't look too bad. That actually looks pretty cleaned up. Oh yeah, here you got the double thing. This is add to do, update to do, improve test, add sanity, add a dummy. Yeah, all right. So now we got what, 200 viewers because I nailed this on the first try? That's amazing. That's amazing. We don't have 200 views. All right. So let's check this out. Okay, so we got this working. Let's remove a bunch of the pseudocode. I want to see something. So if I now look at this algorithm, so we have up and mark here. Let's, there's something to be said about implementing pseudocode by copying it over as a comment and just typing it out, because it maps really well, right? So if def then return killed in block stop. We could maybe copy this, because killed in block stop. Great album name, killed in block stop. Then what is the second condition? By the way, I think we can do this. Yep, now we got this here. Propagation already done, stop. If it's already in here, yeah. Yep. All right, if it's already in here, propagation already done, stop. We can put this in here. Then we add it to live in, otherwise we check if it's in the phi defs. Yep. By the way, do we need these somewhere else? So we can maybe shorten this and say phi defs of block contains will return. Do not propagate phi definitions. Oh, they got the... Look, I copied this from the PDF and it actually turns it into the neat little phi symbol. That's pretty cool. Propagate backward. This is what we do, right? We walk up the whole predecessor chain. which I copy and pasted. Nice. And insert it in up and mark it. So here's a mental note. Where is it? Pretz trees. Here. This is duplicated from the SSA code. So this is, let's make a note here. So I have a file called traversal that has a bunch of stuff to iterate. Sorry. Is it iterate or iterate? Somebody should write this in chat. Iterate, I think somebody told me. Somebody from Canada told me, so there might be regional differences. So depth first DOM tree. This is, a thing, and then I have a bunch of tests on how to iterate over the CFG. And I think Pretz tree should go here. We should extract this into traversal.rs. Yep. So this gives me a Pretz tree, which is, for each block, give me the predecessor IDs. That's pretty cool. And the funny thing is, so it in order to compute the predecessor tree, it actually uses the traversal pre-ordering, right? So it says, walk up the tree. From that tree, give me the immediate predecessors, and from those, give me the immediate predecessor, blah, 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 and it walks those up. But it's pre-ordered, so it says, go up one level, give me these, and then go up one level and give me those. Listen, iterate from Google Transfer. All right, let's do this. Iterate.
Iterate.
Iterate, yeah, it says iterate. So how do Rust people pronounce iter? Pretty sure it's iter. All right. Back to the topic at hand. Where was I? So yeah, this is traversal predecessor tree. That's pretty cool. We should extract this for each use in B. This is live out in B. These are all the reads. So this is, let's add a comment here. So this says traverse B to find all uses. So let's add this as a comment here. Including the uses done by the terminators of the blocks. Final uses, including the uses done by the terminators of the blocks. All right. And then what does it say? Consider all blocks successively used in the phi of a successor block. So mark or iterate over the vars used in the phi of a successor block. That's what this is. Actually, it's not too bad. The code is it's not that bad, right? Looking at it now. I mean, up and mark is a pretty stupid name. But what are you gonna do? This is a ride. But yeah, all right. Let's add some more assertions to our test. All right. So the problem is that my font size is so big that I cannot see the graph. So now we're looking at the same test from two different angles, and we're gonna add some more assertions, and we're gonna learn about liveness. All right. So we asserted that the live out set of B0 has one element. That is correct, right? We can run the test, boom, it passes. Now we can assert B0. And now we can assert that the live in set of B0 should be 0. Live in does not mean these vars are live inside the block. Maybe I'm talking shit right now. But I think it means these are the vars when going into the block. Let's see how we do live in. So we say for all the uses, not definitions, we mark them as live in, right? And we don't have a use of A. All right, so live in should be 0. Again, get ready to clap. I'm going to run the test. Watch this. Fucking hell. All right. So why is live in not 0? Why not? Why not? What is live in of 0? Is it A? Did I misunderstand? Context live in B0 is this. Context live in B0. I was stupid. What? Where is it? What is why is this? Let's exit. All right, let's run this again. Panic no entry for key. Oh, of course. Oh, Connie, I was right. So it's panicking because we there is no entry for a live in set. That's pretty cool. Code right, test wrong. That's exactly right. Yeah, we don't have a live in set. So let's do this. Contains key B0, and we say assert, and we say nah, this should not contain. There should be no B0 live inset. Of course, we can later refactor this and say we always have live insets because it's it's green. Nice. All right, so what do we do next? Check this out. We're gonna do B1. Assert B1. What is live going into B1? Let's do this first. Maybe let's do this. We turn these around. We first check live in because that makes sense. And we're gonna say, hey, B1 should have a live set. So we say assert connects live in contains key should be true. Boom. Here we go. What should be live going in? And we say let A0. We're gonna make this a little thing here. A0, and I'm sure I turned the Clippy warnings off, right? So there will be no complaints. So we're gonna say in B1, in live in, it should it should contains a 0. Live in for B. So the var A is live going into B1. Yes. I cannot believe that this actually works. We implemented this live and it actually works so far. I mean, if it stops working, I'll stop the stream. But, I gotta run in like 20 minutes or 30 minutes anyway. But I'm amazed. We actually implemented liveness analysis live while on stream. That's incredible. So assert B1. What is live going out of B1? So here's B1. What is live? Here's B1. What is live going out of B1? The only thing that is live going out of B1 is D. Because B is only used inside B1. So let's do this. And we say B1 live out length should be 1. All right, let's run this test. Boom. It's green. All right. Let's move this up here. And now we say live out B1 should contain B0. We put all of our places up here. B0. What is going on? Wait, what the fuck? No, I just did. This is stupid. What I just did the opposite of what I said I'm going to do. I just said B is not live going out. The only thing live going out is D. But D, we need to check. This is D, 4002. And 4001 is the D over here. So this is going to be a brittle test. Live out should only have one thing, and that is D. And we say D, 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 D2. D2. Yes. That's amazing. All right, so now we can do the same thing for B2. Assert B2. So B2 has a D1, D1. And we say the live in contains a B. Yeah, we're going to have a live in set for B2. And the live in set for B2 should also contain a 0 because it's live going in. The live out set for B2 should also only be one thing. And that should be D1. Incredible. All right, B3. B3. What is live going in and out of B3? I'm looking at the chat over there. B3. What is live going in? Live in is D. All right, so live in is D. How does the paper, so since D is a phi, live in for each phi use, we're gonna add it to live in. So I'm wondering, I think it's gonna have both D, D1 and D2. So let's see. It's gonna have, so yeah, so the code here says for each phi use, right? So in B3, let's make this fail for a second. So you can see the CFG. Oh, we got the CFG. So in block 3, we have a phi var, a phi function, right? And the phi function says, hey, in 4000, let's put, it could be one of these two values. It could be 4002 version 2 coming from block B1 if we come from block B1, or it could be 4001 if we come from block B2. And now what the paper says, it says for each phi use in B, so these are the phi uses, the operands of the phi function. We're gonna add them to the live outs. Wait a second. Used in the oh no, this is, wait a second. For each, if we find, let's see, I'm not sure. I would say the phi operands, they should be live going in, right? Should be 2 in the live in set. Let's see. No, I think there should be 2 vars in the live in set for B3. fails. We don't have a live inset for B3. How does it do this? How does it do this? What does it do with the phi operands? I mean, it says here all the phi uses, but then it says phi excluded. So this is why we don't add it to the live inset. We only put them into the live outset. So what? Okay, so let's check something here. So do we have a live outset? Of course we should have a live outset. No, the live outset. Does Rust have a certain no? We shouldn't have a live outset. Yeah. Because no var E is not used. Like if we would do this, sorry. And we say we have a P4 and then we say F and it's E, then B3 would have a live outset. Let's do this because I think this is a good addition. I'm just wondering why. I'm wondering whether I did this wrong. For each V used in B. That's the proofs. Correctness, yeah. Phi uses. So that's the other version. That's the other algorithm. So live in B should be the phi defs of B. Union we denote phi defs B, the variables defined by phi operations at the entry of block B, and phi uses the set of variables used in. So the phi defs, so live in should be 4000 like D0. So there's a bug. That should pass. Why not? I don't get it. Where do we print this, by the way? There's some printing going on. Yeah, this. There you go. Live out, live in. We only have 1 and 2. So something is fishy. First of all, let's remove this. Live in should contain a key, so this test is still failing. All right. I mean, this clearly says defy defs, so basically this one should be in the live inset of this block. But if we look at the algorithm again, where is it? Data flow 5, it's in 5, section 5, 5. There you go. So where would it do this? So for each basic block in CFG, so each block here, for each phi used in the successor. So this is exactly what works, right? So this is why in the live outset of B1 and B2 is this D. So that works. Oh, no. No, for each V used in B. So D is used, right? D is used. Aha, so I'm wondering whether it's something like this. This is maybe wrong. So let's trace something here. Where's our up and mark here? And we say if place. Oh wait, where do I have this? If place equals place version register 4000 0. What the? Come on, the trade bound. So I'm trying to debug something. Here is D. And we say here's D. Let's say block V, which we have, and we say block ID V. Here's D. So, oh ho 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 ho! What? There you go. Whew. All right. So this says if definitions phi excluded, and I said something's fishy going on here. And this is the problem. We need to say filter I is phi func. So this is what we forgot. So we want to mark D as live in, right? But we said, oh, is it defined in B? Then it's not live in because it's defined in here. But we forgot this and say, if it's defined in here except in a phi function, because if it's defined in a phi function, then it is very much part of the live in set of this block, which is what the definition, scrolling up, what the definition, come on. What the definition, Jesus Christ, live in, there you go. What the definition says. The definition says live in a block B are the definitions, the things defined by a phi function or by d phi functions in B. Boom. Boom. I'm so happy that you also appreciate this. This now makes me want to stream more often. People actually emoji clapping. Sweet. All right, this was good. I started to sweat. All right, let's do this and then we can call it a day because we actually, boom, this was good stuff. We actually implemented this. Well, gonna need to add some more tests. I also need to take a sip of water. Should mute me. Waiting for translation. Please stream more often. Yeah, I would love to stream more often. The problem is, Saturday morning is a time for me that I can do this, or Sunday morning sometimes. But other than that, weekdays I hack on my compiler stuff from 6:15 to 7:30 in the morning with my workout clothes on. So you don't want to see me on stream. And then, usually then I go work out and then I work and then family dinner and whatnot. And then I'm usually pretty beat to do some more streaming. So it's hard to find a time slot, to be honest. In the evenings would obviously be the best for all time zones considered, but yeah. Running 0 tests. What? No, this is okay. Test pass. So live in contains now. Oh, here's the actual real assertion, right? So what we want is D0 to be live in. D0. The live in set assert live in B3 contains D0. Assert this. Live out set should be empty. Boom! It passes. I cannot believe this. Nice. That's pretty cool. We actually did it. Morning stream with just voice will also work, I think. That could be an option. Or just the lights out and it's really dark in here. All right, boom. Let's make a commit. And let's say, actually, probably, maybe implement Liveness Analysis. Push this up. So now, what I want to do is, let's do another thing. Let's do another. Let's do another test. Live sets. Consecutive. Is it though? Series of blocks. What do you use to make the diagram between the code? On the Mac, I use Monodraw, which is pretty cool. It's really, really cool. Like, this is $9 now. You should buy this. So this is really cool. It doesn't work on Linux though, but you can write stuff in ASCII and move stuff around. Yeah, so you have these interactive lines and you can move them, and it's pretty neat. And then you just, oh, what? That's new. It's $10, but come on, it's $10. So this seems new. Anyway, so I used this on a Mac, and then I copied in the source files, and then I just modify it by hand here in the editor. So what I want to do is, there's also this. There's Venn NVim. Somebody linked me to this yesterday on Twitter. So this seems also pretty cool. Yeah, I think this is the one you mean, Connie. It looks pretty similar. It uses the same style. Yeah, that's pretty cool. But you know what? For all my purposes, did you move to NVim? Yes, I did move. Yeah, it's much. I don't know what exactly changed, but it feels much nicer. All right, so back. That's right. So yeah, I use Vim comp. Yeah, that's this one here. So let's say we have a graph like this. And this is nice exercise. And then we delete this one. Oh boy, they're not super aligned, right? Oh boy. Wow. So this is, let's say this is B1. And then we have B3. That's a good test. All right, so let's try and make this. So in A, we have which registers do we need? We need A. Let's call this C then. It's A and B, and this is C, and this is D. So we don't need E for now. We need 2 temp registers, because the temp registers is what the compiler or the IR builder currently emit for a binary instruction. So instead of saying take this, compute it, and put it in here, what it does is it says take this, compute it, put it in a temp register, and then do a move instruction and move from one temp to the other. So let's align this like this. Something feels off. You know what we could do? Like this. So I cannot believe there's people watching me do this. Well, I can, but I'm sure if I tell somebody in the so-called real life, hey, this morning I actually streamed on Twitch, and you know what? People watched me move ASCII characters around the screen. And it was beautiful. And people cried and they hugged, and they enjoyed this. And everybody was happy. Everybody was content. So, okay, here's a question. I'm going to embarrass myself. VOD, VOD, what does it stand for? Video. Is it just video? Is it like a typo thing or whatever on VOD? Video on demand. Okay. I didn't want to say this because it's such a 90s term or 2000s term. And I didn't want to date myself, but video on demand. All right. Yeah, I think I'm going to keep this video for this actually because we're now 1.5 hours in and we implemented liveness analysis. Huh? That's pretty cool. Gonna put this on my CV and say, hey, you want to see me code? Watch this. All right, so we got this B1, B2. We got D, 2 temp registers for the 2 binary instructions. Let's take this. I think, yeah, the stream stays on Twitch for a month, but I think I also got a YouTube channel somewhere so I can export this, I think. So add entry block with instructions. So we move so here we now have to build this by hand. And then in B1, yep, this is wrong, right? We move 22 and we say move into temp and then move into C, temp 1. All right. Oh, there's an off by 1. Then we have B2. And in B2, we don't have this one, but we say move C plus 5 into a temp and temp 2 and then move that into D. Right? And we don't have any other thing. We don't have this, but we say terminate go to. We go from B1 to B2, and we go from B2. From B0 to B1, and then we go from B1 to B0. But from B1 to B2, I don't know why I said 0. Why are my inlay type hints off here? Is this LSP restart? Boom. All right, so we need to set up the func assigns. Okay, so A is assigned in B0. There's no other assignment. B is assigned in B1. There's no other assignment. C is assigned in B1. And then D is assigned in B2. All right, and we got the temp ones. Temp is assigned in B1. Temp 1 and temp 2 is assigned in B2. Boom. We don't got any more assignments. All right. So then we do analysis, blah, blah, blah. And now we can do the assertions, right? We can do the assertions. Let's delete those. What is going on here? Let's restart this for a second. Oh. Trading white space. Can't commit this. All right. There you go. All right. So now let's do these assertions. Let's copy one of these over. Sorry, I deleted this. We say assert, and let's move up here so we can see all of this. So what is live in B0? B0 should not have a live inset. All right, but it should have a live outset, and A0 should be in a live outset. Let's run this. It doesn't. Assertion fail. Live in. What is going on? What is going on? What is going on? For be live in context, live in print and now live in BID. Oh, it is ID live in. Yeah. Okay, all right, I got it. Oh. There's something funky going on. It says D is live. So it says live in of 0 is registered 3000. Because and that is C. What? What is going on? I think the setup is wrong. Something here is wrong. Let's print the function. All right, A, 1000, boom, 0. Then we go to block 1, boom, ancestor is 0. We say B, 2000, right, is 22. Then we say temp 1 is 1000 plus 2000, so it's A plus B. Move that into temp 1, and then we say C 3000 is temp 1, and then we go to 2, and then we say 3000 plus 5. Move this into temp 2, and we say 7000. Move that into 4000, which is D. So what is going on? So, I mean, A should be live going into B1. That's correct. Why the hell is C not live? Is in the live in? Where is C? Here. Wow. All right. Bye-bye, Connie. I'm also going to hop off in like 10 minutes. Actually, you know what? I should hop off right now so I have a failing test to come back to. Context live in contains B. Live out. The live out for 0 is, it somehow thinks that the C is defined somewhere else. Why? I don't get it. I really don't get it. So, why does it think that C is defined here, 3000. So here we have a use of C, and then it walks up. And then it says, boom, it was defined in here. No need to go further up. You know what? Let's okay. We're gonna give this 10 more minutes because I really need to hop off. So that we can remove this debug stuff, and we say, up and mark. This is puts debugging, print debugging, and we say block is this and v is this, and we say block ID v, right? And then we say print nl, print ln, not nl, ln, and we say killed in the block, and then we say already done, and then we say phi defs contain v, and then we say propagating backward. All right. Here we go. Up and mark block 2. 3000. What the? Block 1, 3000. Killed in the block. That's right. That's right. But why does it do? Oh. 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 So this doesn't stop. Oh boy, so it walks up the predecessor chain. And if the first one says, that's interesting. All right, so let's hack some stuff here, and we say this returns a bool, and we say return false, stop, and this also says return false, stop, and this do not propagate. This also says false. And then here it says return true, I guess. And it says if up and mark, if it's false, return false. Why? What if it's not up and mark? Oh, yeah, okay. Yep, all right. So now let's run the test again. Oop. Now it passes. We got it. All right. Okay, cool. So we didn't stop propagating. Let me add a to do. This is not great. We use the bool only to say whether we should stop walking up the predecessor chain. There has to be a better way. There might not be a better way actually, but writing to do down to consider this. What is this? 4? Did I make a typo? Where did I make a typo? All right, let's add two more assertions. So this is our test, and we say the life in, we don't want the life in set. The life out set for B1 should only contain one thing. Then let's do this. We say assert B1. We do want the life in set. And the life in set should be A. We want to say life in for B1. For B1 contains A 0. Let's see if this runs. Tests pass, should pass. All right, so Mick Mine joined, and the question is, what are we doing today? So we're wrapping up. What we did was implement liveness analysis in my toy compiler. And I'm just adding a test. So live in going in B1 is A, right? What is live going out? Live going out of B1 is C. So we say we want a live outset for B1, and the live outset for B1 should contain Z0, and Z0 should be this. Let's see if this passes. It passes. And then we want to do the same assertion for B2. And we want to say B2. Let's replace all B1, B2. So like a health check. No, so liveness analysis looks at source code and says which variable is live, meaning will be used at a certain point in time. All right. So yeah, that's no. I need to finish this. I really need to hop off in a second. So we want a live in set for B2. We don't want a live out set for B2 because there's nothing coming after B2. And the live in set should contain Z0. Z0. Check it. Boom, and it passes. Sweet. And with that, I'm gonna make a commit and say clean up, add another test, add another liveness unit test, and then we say up it is. And with that, I'm gonna say thank you for watching, and this was a lot of fun. We actually managed to do it. We implemented liveness analysis. Next up is cleaning up, refactoring, adding more tests, and then live ranges. All right. And with that, bye-bye. And I'm gonna stop